As you can see on the slide, we have 6 types of enthalpy. But for this chapter, only focus on A, B, C only, which are the enthalpy of formation, enthalpy of reaction, and enthalpy of combustion. And then class, standard state condition for measuring the enthalpies are, the first one, the temperature must be at 25 degrees Celsius or 298 Kelvin, and then the pressure is 1 atm or 101 kilopascal, and the solution having concentration of 1 molarity. Standard enthalpy of formation is the enthalpy change, heat liberated or absorbed, when 1 mole of a pure compound is formed from its element at a standard condition. The standard enthalpy of formation of any element in its most stable form is 0. For example, oxygen O2 is 0 because it is in stable form, whereas ozone O3 has a value of 142 kJ per mole. Carbon in graphite is also a stable form as compared to carbon in diamond form. Compounds with negative standard enthalpies of formation is exothermic compounds. Compounds with positive standard enthalpy of formation is endothermic compounds. This table provides the values of standard enthalpies of formation for substances at 25 degrees Celsius. You can always refer to this table to get the standard enthalpy if the exercises not provide you with the value. Don't forget that elements in its most stable form, the value of standard enthalpy is 0. Standard enthalpy of reaction is the enthalpy change of a reaction carried out at standard conditions. Standard conditions are the reaction is carried out at 25 degrees Celsius, pressure 1 atm, and concentration of solution is 1 molarity. Let's discuss on this example. Consider the following reaction. 1 mole of hydrogen react with half mole of oxygen, produce 1 mole of water molecule. The standard enthalpy change is negative 287 kJ per mole. A. Is the reaction an exothermic or endothermic reaction? The reaction is exothermic reaction. This is because the value of standard enthalpy change is negative. B. Is the total enthalpy for the reactant larger than the total enthalpy for the products? The answer is yes. It is an exothermic reaction. Reactants have more energy than the products, so it will release the energy to products. And C. What is the value of standard enthalpy change for the reaction? 2 mole of water molecule produce 2 mole of hydrogen plus oxygen. The answer is 571.6 kJ per mole. I hope you can try to calculate the answer by using the formula we discussed in the previous slide. Enthalpy of combustion is the enthalpy change when 1 mole of pure substance is completely burned in excess oxygen under the given temperature and pressure of the reaction. If the conditions of the reaction are standard condition, then it is called the standard enthalpy of combustion. The value of standard enthalpy of combustion is always negative because it is an exothermic reaction. The equation in slide is an example of combustion reaction between 1 mole of methane with 2 mole of oxygen produce 2 mole carbon dioxide and 2 mole of water molecules. The value of standard enthalpy of combustion is negative 890 kJ per mole. In this example, we need to use the thermochemical equation given to relate the mass of reactants and product to the amount of enthalpy released or absorbed by the system. From the equation, 2 mole of sulfur dioxide reacts with 1 mole oxygen to produce 2 mole sulfur trioxide. The enthalpy change value given is negative 198.2 kJ per mole. The question requests us to calculate the heat evolved if 87.9 grams of sulfur dioxide with molar mass of 64.07 gram per mole is converted to sulfur trioxide. First, from the mass given, we need to calculate the number of moles of sulfur dioxide in 87.9 grams of the compound. Then, find the number of kilojoules produced from the exothermic reaction. In the lab, heat changes in physical and chemical processes are measured with a calorimeter, a closed container designed specifically for this purpose. The change in temperature of a substance when it is heated or cooled depends on the heat capacity of the substance. Experimentally, we can determine the heat flow, delta H reaction associated with a chemical reaction by measuring the temperature change it produces. Calorimetry is a method for measuring the heat change of a reaction. An apparatus that measures heat flow is called a calorimeter. A calorimeter consists of an insulated vessel in which a chemical reaction or physical change is allowed to take place, and the heat released or absorbed is measured. There are two types of calorimeter: bomb calorimeter and simple calorimeter. So, before we discuss more on the calculation related to calorimetry method, we need to familiar with few important terms. The first term is specific heat of a substance. The symbol is C, or sometimes we can also use S as the symbol. Okay, specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius, and then the unit for specific heat is joule per gram degree Celsius or joule per Kelvin, joule per gram Kelvin. Next is the heat capacity of a system. Okay, the symbol for this is capital letter C. It is the amount of heat required to raise the temperature of a given quantity m in grams of the substance by 1 degree Celsius, and then the unit is joule per degree Celsius or joule per Kelvin. Okay, please don't get confused between the specific heat and heat capacity, since the specific heat will tell the amount of heat to raise 1 gram of substance, and heat capacity will tell us the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree Celsius. Okay, specific heat and heat capacity do have the relationship. Okay, to calculate the heat capacity, the capital letter C, okay, we need the specific heat. The formula of heat capacity is mass in grams times specific heat. Okay, here we have an example of specific heat for water. The value is 4.18 joule per gram degree Celsius. Okay, it means that 4.18 joule is needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, now let's continue with the heat formula Q. Okay, so amount of heat Q transferred to a substance or object depends on the mass of the object m in grams, its specific heat C, and temperature change delta T. Okay, the formula of a heat Q is Q equal to m times C. C is the specific heat times delta T. And then we can also simplify the formula to Q equal to C. This one is capital letter C, refer to as heat capacity times delta T. Okay, this is an example on how to calculate Q. Okay, let's read the question first. How much heat energy is released when 7.1 grams of substance is cooled from 100 degrees Celsius to room temperature 25 degrees Celsius? The specific heat of the substance is 0.460 joule per gram degree Celsius. Okay, in this case, the questions want us to calculate heat. Okay, this is heat, is Q. And then we are given the mass of the substance 7.1 grams, and then 100 degrees Celsius is the initial temperature and the final temperature is 25 degrees Celsius. So the formula for heat is Q equal to mc times delta T. We have mass of substance in grams, and then we have the specific heat of the substance, and also we can calculate for delta T. Delta T is T final minus T initial. So we can substitute now the value to the formula 7.1 grams times specific heat of the substance 0.460 joule per gram degree Celsius times 25 minus 100 degrees Celsius. Okay, final temperature, this one, minus initial temperature in degrees Celsius. So the value is negative 245 joule, the value of heat. So negative means the process is exothermic process. Okay, so heat is released. Okay, now let's continue with calorimetry method. There are two types of calorimeter. One is simple calorimeter, or we call it as coffee cup calorimeter. We conduct this experiment under constant pressure. And another one is bomb calorimeter, and the condition is under constant volume. Calorimetry method is a technique used to measure the heat exchange in chemical reaction, and a calorimeter is a device used to measure the heat exchange. Okay, how to determine whether the reaction is exothermic or endothermic? If the temperature is rise, so the reaction is exothermic. And if the temperature of reaction goes down after the experiment, it means that the reaction is endothermic. The concept of calorimetry is no heat in or out from the calorimeter, so the wall must be insulated. In simple coffee cup calorimeter, usually we use polystyrene cup because it has a good insulator properties. It is good to prevent heat from experiment to escape to the surrounding or the other way around. Okay, now we are going to discuss on a bomb calorimeter. Okay, as you can see on the slide, this is a cross section of a constant volume bomb calorimeter. Constant volume refers to the volume of the bomb which does not change during the reaction. It consists of a very strong vessel, this one, very strong vessel, surrounded by water in a container. Okay. This calorimeter is suitable for determining energy changes in a reaction such as combustion reaction. Okay, this is conducted by placing a known mass of a compound in a steel container which is filled with oxygen. Okay, we fill the steel bomb with oxygen. The closed bomb is immersed in a known amount of water, and then a known mass of sample which placed in a sample container is ignited electrically with the ignition coil, and the heat produced by the combustion reaction can be calculated accurately by recording the rise in temperature of the water, because the heat given off by the sample is absorbed by the water and the bomb calorimeter. Water, okay, this one, water and the metal parts are considered as the surroundings. Okay, so we need to know some basic principle of the bomb calorimeter. Heat released by a reaction equal to heat absorbed by the surrounding. So in this case, surrounding is water and metal parts. Metal parts is the steel bomb. So the formula is heat released by a reaction equal to heat absorbed by water plus heat absorbed by calorimeter, which is referred to the surroundings. So the Q of the reaction equal to negative Q of the calorimeter, which is the steel bomb, plus Q of the solution, which is referred to water. Okay, let's look to the equations we have here. Heat of the system, Q of the system, equal to Q water plus Q bomb plus Q reaction. Then we have here Q system equals to 0. Why it is 0? This is because the system is insulated. Okay, the special design of the calorimeter allows us to assume that no heat is lost to the surroundings during the time it takes to make measurements. The system is isolated because no heat enters or leaves the system throughout the process. The heat change of the system must be 0. Okay, then we rearrange the formula in order to calculate the heat of reaction. Okay, so we get here Q reaction equal to negative Q water plus Q bomb, and then Q water, as we already discussed the formula before for the heat, equal to M times C of water. C is the specific heat times delta T. And then Q bomb equal to heat capacity C times delta T, change in temperature. Okay, the reaction in bomb calorimeter at constant volume, enthalpy change is not equal to heat of reaction. But since the specific heat for solids or liquid is assumed constant with pressure and volume, therefore, we can assume that enthalpy change is equivalent to heat of the reaction. From the basic principle, we know that heat release equal to heat absorbed by water plus heat absorbed by calorimeter. The formula is Q equal to M times C times delta T plus C prime times delta T. The formula is simplified until we get Q equal to C times delta T, where M is mass of water in grams, lowercase c is specific heat capacity of water, C prime is heat capacity of calorimeter without water, capital letter C is heat capacity of calorimeter with water, and delta T is change in temperature. Calculate enthalpy change of reaction or combustion in calorimeter. There are two situations we need to discuss in order to calculate enthalpy change of reaction or combustion in calorimeter. Situation number 1, when the value of heat capacity of calorimeter is not given in the question. In this case, we must assume calorimeter is totally insulated, which it do not absorb or release heat from the reaction. Heat released by reaction will only absorb by water. So, heat of reaction equal to negative heat of solutions. Since we don't have the value for heat of calorimeter. So, heat gained by water equal to heat lost by reaction. Situation 2, where heat capacity value is given in the question. It means that calorimeter will be able to absorb or release the heat from reaction. Therefore, heat released by reaction will be absorbed by water and calorimeter. So, this is the formula for situation with given heat capacity Q of reaction equal to negative Q from a calorimeter plus Q from water. Here is an example of enthalpy change problem to calculate where the data was collected from bomb calorimetry method. Hope you guys can try to solve this problem. All the best. This is another type of calorimeter we want to discuss. Simple calorimeter or coffee cup calorimeter. It is suitable for measuring enthalpy change for reactions that take place in aqueous solution. The outer polystyrene cup insulated the reaction mixture from the surroundings. It is assumed that no heat is lost to the surroundings. Basic principles of this calorimetry are heat released by a reaction equal to heat absorbed by the surroundings, and heat released by a reaction equal to heat absorbed by solution plus heat absorbed by calorimeter. The formula for heat of system is equal to heat of solution plus heat of calorimeter plus heat of reaction. Because of the system is insulated, so heat of system is 0. Then the heat of reaction equal to negative heat of solution plus heat of calorimeter. Heat of solution can be calculated by mass times specific heat of solution times change in temperature delta T, whereas heat of calorimeter is heat capacity of calorimeter times delta T. Reaction at constant pressure, enthalpy change equal to heat of reaction. From the basic principle, heat released from the system equal to heat absorbed by solution plus heat absorbed by calorimeter. For simple calorimeter, heat capacity of calorimeter is very small. So, from the equation, C prime delta T can be removed from the heat equation. We just consider the heat absorbed by the solution. For aqueous solution, the density and specific heat capacity are usually assumed to be the same as for water, 1 gram per ml for density and 4.18 joule per gram degree Celsius for specific heat capacity. Let's discuss this example. A lead pellet having a mass of 26.47 grams at 89.98 degrees Celsius was placed in a constant pressure calorimeter of negligible heat capacity containing 100 ml of water. The water temperature rose from 22.5 degrees Celsius to 23.17 degrees Celsius. What is the specific heat of the lead pellet? Constant pressure calorimeter is a simple calorimeter or coffee cup calorimeter. Don't forget that calorimeter is an isolated system, means no heat loss to the surroundings. The equation is heat of lead plus heat of water or solutions equal to 0. So, heat of lead equal to negative heat of water. The heat gained by the water is given by heat of water equal to mass times heat capacity times change in temperature. Now, substitute the value given in question to the equation. Heat gain by water is 280.3 joule. We want to find specific heat of lead pellet. Because the heat loss by the lead pellet is equal to the heat gain by the water, so heat of lead equal to negative 280.3 joule. Solving for the specific heat of lead, we write the equation heat of lead equal to M times C or S times delta T. So the value for the specific heat is equal to 0.158 joule per gram degree Celsius.